Take it to record. Okay, so I want us to continue from where we stopped from, and I had issues with my slides last time, but I think we will be able to follow up from there. Now, we have already seen in the previous lecture, we saw clearly that period 4 are smaller, while period 5 and 6 are large. Reason, when you move from period 4 to 5, you've added an extra period or an extra energy level, and therefore period 5 are bigger. That's why scandium is bigger than yttrium, or that's the reason why titanium is bigger than zirconium. Sorry, that's the reason why zirconium is bigger than titanium. I'll repeat. I think I've made an error in my explanation, so allow me to repeat. So I've said we previously saw, or even from this table, it's very clear for us to see that we have a group period 4 being smaller. It is here. Then period 5 and 6 being larger. Okay. So the reason why titanium is covalent radius is 32, whereas that of zirconium and hafnium is around 45, is because as you move from period 4, period 5 and 6, you are adding on more and more energy levels. Another thing we've also seen is that period 5 and 6 elements have so close or similar covalent radius. Okay, why are they so similar in size? And that is what we were to answer before we broke off. Now, why? Because the filling of 4f orbitals is accompanied by a steady contraction in size at the point where the FD orbitals begin to fill. The radius have decreased to a similar size to that of elements in the previous period. I'll explain this uh, uh, just here. So when you have period 4, period 6, you have period 6 there. So we expect period 6 will be bigger. Ordinarily, we expect this may be something like this. Period 5, and this to be period 6. So we expect period 6 to be bigger. But in reality, what do we find? We find both of them being of the same size. This is what we see in reality. This is what we expect, and this is the reality. Why is the reality like that? It's because when you are in period 6, you start filling the 4f orbitals. And when you're filling the 4f orbitals, contraction is happening. The atom is shrinking and shrinking, such that by the time you start to fill the 5d orbitals, it has shrunk so much that filling the 5d orbitals does not make its size increase. Okay. Of course, you can rewind my explanation. I don't have to repeat it. Given that it's recorded, you can always unrewind it and listen to it. So that is the reason. So this decrease in atomic size that results from the filling of the 4f is called the Lanthanide contraction. Okay. Similar sizes of so I have had network issues, but I hope we are still on. So let me share again my slide. I hope it will be consistent enough. So again, you'll excuse me for the background noise from the kids, but I hope you'll still be able to understand. Now, I'll repeat again the reason why the period 6 and period 5 elements have the same radius. And the reason is usually referred to as what we call the lanthanide contraction. So let's start again. In reality, okay, in reality, we expect, let me use my pointer. So in reality, we expect that the radius of group period 6 will be bigger compared to period 5. But remember, period 6, you feel orbitals in period 6. Remember period 6, how it looks like. In period 6, you have 5D and 6S. But before that, you have 4F. Okay. So when you get to period 6, okay, what will you start with? Filling the 4F orbitals, okay? And when you start filling, so period 5 has the 4F orbitals, okay? It has, but period 5 has no, it doesn't have F orbitals. So this one has no F orbitals, okay? So when you reach period 6, you start filling the 5F orbitals before you fill the 5D and 4S. So during the filling of the 4F orbitals, the atom contracts steadily, okay? Contracts and contracts until the size is so small, okay? By the time you start filling the 5D orbitals, the radius has decreased almost to the size of elements in the previous period. That is in the period which is period 5. So in reality, we expect this, but sorry, we expect this S6 to be bigger, 5 to be smaller, but in reality, they are the same. Why? Because of the lanthanide contraction, which I've just explained there. So this decrease in atomic size that results from the filling of the 4F orbitals is called lanthanide contraction. Electrons added to the same F orbital plus increase in protons. So similar sizes of the second period and the period 6 series D block elements have significant consequences for their chemistry. So when you find elements in period 6 and period 5 having similar or the same atomic radius, okay, this also implies their chemistries are a bit similar. So the first one is our platinum group metals. So where are our platinum group metals again? Let's see where they are. Yes, our platinum group metals are simply this block I've written in red, this one. Ruthenium, rhodium, platinum, silver, gold, platinum, iridium, osmium. Their radius is so similar and their chemistry is so similar. They are usually mined even from similar ores. Okay, let's see the other implication. What makes, if they have the same radius, what will happen to their chemistries? Okay, so they form similar compounds. We are here. Minerals containing these metals are found in the same geographical zone and in the same ore. For example, zirconium and hafnium, they have the same radius, okay, but different periods, okay, and they are found in the same geological region and the same O. And that makes it difficult to separate them during the mining process. Elements in the period 4 have substantially different properties from elements of the same, of the same group in the 5th and 6th period. Ordinarily, you expect elements in the same group to have the same chemistry, but this is not the case. So again, I'll go back to explain this just up here. I want us to go slowly and see. Okay, let's that. Okay. Now, what it means is this, that, for example, elements might be in the same group, but their chemistries are totally different. So look at these two. Okay. Or even let us look at these two here. They're in the same group. Okay. But the ones in period 5 and 6, for example, silver and gold, they have the same or similar chemistry. But this one, copper, which is in period 4, the chemistry is not similar. Why? The radius, okay? The radius of silver and gold, same or similar, very close. And therefore their chemistries are so close. Whereas for copper, it is a bit different, okay? It's not so similar to silver and gold. So the chemistry of those two is totally different. The same story if you talk about maybe something like chromium here. Molybdenum and chromium. Molybdenum and tungsten W, same size. Chromium, different size. Again, their chemistries are not so similar. Okay. So again, remember I said about this, hafnium and zirconium and titanium. So zirconium and hafnium, okay, those two. Let me clean. I know some daydreamers might not be seeing clearly. Okay. So this there, those two, okay. Okay, let me use the cursor now. Okay. Something is again a miss, but it's fine. But all of us know titanium now. I don't think if you don't know titanium now, everybody knows what is titanium. So titanium is totally different from zirconium and hafnium in terms of their chemistries, even though they're in the same group. If we remember main group elements, for example, potassium and sodium, they're in the same group, same chemistries. But here in transition elements, things are not like that. Okay, so I'll move on. This decrease in atomic size across a row is usually observed in main group elements. It is due to the increase in effective nuclear charge that acts on the outer electrons and pulls them in more strongly. Effective nuclear charge is the positive charge felt by an electron. It equals to the nuclear charge minus the shielding or screening of the positive charge by intervening electrons. So effective nuclear charge increases as you move from left to right. Okay, from left to right. And that's why you see a gradual dip in the radius. You see a gradual dip in the radius like that. If you are here and you're moving across like that, if this is your radius, okay, and you're moving from, let's say, we start with group 3B, then group 4B, group so on and so on. And when you reach somewhere, it starts again rising. But the dip we are seeing, okay, the dip, you know what is a dip? A dip means a decrease, okay, or a valley. So the dip we are seeing here we are actually seeing a dip here. Just look at this. So we have this trend. It's dropping, the radius is decreasing, 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 decreasing. Okay, so how do you explain that decrease? It's because of the increase in effective nuclear charge. Why? Because you are adding electrons to the same energy level. So when I move in one period, okay, I'm just moving across one period like that, like that. Okay, you can see. So for period 4, I'm moving like that. So I'm moving from group 1, group 2, group 3, group 4, group 5, group 6. So I have the same, the outermost energy level is 4. And in that energy level, I'm adding what? Electron. So it is my D. I add 1 here in scandium. Then I get to titanium, I add 2. Then I get to vanadium, I add 3, and so on and so on. And that is what is causing increase in effective nuclear charge, leading to shrinking of the atom. And that is where we are explaining the dip in atomic radius. So let's see the variation in the density of transition metals. Density varies with radius. Okay, so when radius decreases, density increases, means you are packing many things in one space, in a little space. So density, the variation in metal radius causes density of transition metals to increase and then decrease across period. Although the overall change in radius among these elements is small, the effect is magnified because the volume is actually changing with the cube, okay, radius. The lanthanide contraction explains why elements in the 6th period have the highest density, because they are much smaller actually. They get smaller. So what are we experiencing? We are experiencing something like this. We are seeing radius, instead of radius increasing, we are seeing the shrink, okay, down the group. Okay, that is a group. You get, as you move down the group, it is getting smaller and smaller, which is the reverse of what we see in main group. In main group, when you move down a group, you find the size increasing like that. But in transition, the size shrinks. Why? Lanthanide contraction, which we've already seen. And therefore it means as I move down the period, okay, no, sorry, when I move down the group in transition metals, density increases because I'm packing more heavy particles together. They're heavy but small, so I'm packing them together. Remember, when you move down, even the atomic number is increasing here. So we're expecting this will be smaller but still heavier. This one will be bigger but heavier. So when for ordinary main group, density will be decreasing as I move down like that. But for transition, as I move down, density will increase. Okay. Relatively small radius of period 3 transition metals, combined with the fact that the atomic masses are considerably larger than those in the 5th period, causes 6th period metal densities to be very large. I've just talked about that, so it is just a repetition that this, as you move down, your metals are getting heavier. This is period 5, 4, 5, and 6. So the period 6 is heavier but smaller, okay? So it means I'll pack many of this in a smaller area, but fewer of this in a bigger area. So the density will become higher for the lower ones. Those are in period 6, and that is what the whole of this sentence is talking about. And it is clearly reflected here, so that I'll just try to ensure everything is seen. Okay, let me make it a bit smaller. So you have to see clearly that the first part here, the pink, is for period 5, then period 3, sorry, that is for period 3. The first one there is for period 3, then that one is period 4, then that one is for period 5. So all through you can, if I pick one group, okay, group 1, which is scandium and other members, in this period 1, who is in period 1? Period 1 is scandium, Y, and Lu. Scandium, Y, and Lu, okay? So if I pick period 1, which is here, of course, is scandium, Y, and Lu. Then period 2, of course, is titanium and hafnium, I think, and another one there. So that is for period 3. Then this is for period 2. So all through you see that the elements in period 6, period is supposed to be period 4, sorry, 5, and 6. Elements in period 6 represented by the blue bar is usually the highest density so far. So it means all the way they are having the highest densities, followed by the ones in green bars, which is period 5. Then the ones with the lowest density are the ones with the pink for every group, a group at a time. So for daydreamers, you'll have to read clearly. So like the whole of this is one group, okay? The whole of this is another group, okay? Then the whole of that is another group. So every bunch of 3 is a group, a group, a group. And in each group, you find that period 6 have the highest densities. Okay. Variation in melting point. So if something is denser, okay, compactly packed, then it could have an implication on melting point, but let us see what the story says. But again, melting point also depends on bond strength, okay? Melting point indicates something on the bonding strength. Melting points rise to a maximum around the middle of the series, then they descend. What is the middle of the series? They're just saying that in the middle of the periodic table, we have maximum melting points. At the middle of the periodic table, you have maximum melting points. And we're talking about which periodic table? The periodic table of transition metals, not all elements, but just for the transition metals. And you can see that clearly in this graph, okay? This is group 1, group 2, group 1, of course, is those 3. Sorry, group 3B, supposed to be group 3B. Then this is group 4B. But each group, as we see, generally, we see that as we move towards the middle of the periodic table, we see the melting point increasing, okay? Another thing we see is that sixth group tend to have, the sixth period elements tend to have the highest melting point in every group. You can see here, you can see there, you can see here, you can see there, here, here. In every group of the periodic table, period 6 elements tend to have a higher melting point. Let us see the reasoning behind it. or the reason behind it, not the reasoning, but the reason behind it. So, okay, that's the reason behind it. Okay. Why? The variation in melting point indicates that the strongest metallic bond. So remember, we are dealing with metals, okay? So what does it mean? It means the strongest metallic bond occurs when the d orbital is a half filled, okay? So again, it's so straightforward. If we must always be putting our periodic table in mind. The periodic table of transition elements. Forget about the rest, but this is the periodic of the table of the transition element. And when we get to the middle, where is the middle? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 is in the middle. 4 and 5, is it? Yeah, 4 and 5. This is our middle. So that we have 4 on one end, 4 on the other end. So this is the middle of the periodic table. And remember what we saw in the melting point, the middle have the highest. So at this point, you have the highest melting points. Manganese and iron have the highest melting points in this period. Then in this other period, which one have the highest melting point? Tc and Ru, that is technetium and ruthenium have the highest melting point. What about that period? Ruthenium and osmium. Then lastly, there, these two, okay? So we are being told, in this case, it means when you have D5, remember here, that's when we start having D5. Just look at that. That's D5 half filled, and this is also almost half filled. So those two are D5s, okay? And they're almost in the middle of the periodic table. So elements in the middle of the periodic table, of course, these ones, but most likely the D5s, these ones, have the highest melting points, okay? So, of course, carry that at the back of your mind because I cannot move with you everywhere. I have just to ask you again to carry that at the back of your mind and see what is happening. Who has the highest melting point? Is it the middle exactly? 1, 2, 3, 4, 5. 4 and 5 have the highest, as you can see, and even 3 here. Okay, so it's 3, 4, 5 are the highest. And it's mainly because of the D5 there and the D5 here. This is D6. So we are being told that when you have half-filled d orbitals, the metallic bond is strongest. This is also the point at which the largest number of electrons occupy the bonding molecular orbitals. So remember, if you have a D5, okay, if I have half-filled D5, like that, 1, 2, 3, 4, 5, then it means another atom can come there, another atom, another atom, another atom, another atom, so that I have a bond. 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 Okay, I have a covalent bond. So I'm using those dots to represent another electron. So you can have 2 electrons, and when you have 2, this is equivalent to a bond. Okay, like that. So when you have half filled, that's when bonding will easily form, and therefore you have the highest number of electrons occupying molecular orbitals. But imagine when you have them filled, okay? Assume you have this filled like that. Then you have this also full. Then you just have, uh, let me rub it. So let me redo it so that enough space to redo it. So assume a case where you have 1, 2, 3, 4, 5. If you have 5 like that, then they are filled partially, not D5, but just filled, maybe D6. Okay, D6. So if it's D6, how many bonds will you form? Just 4 bonds. But here, which was everything empty, you'll form 5 bonds. So remember here, you'll just form 1, 2, 3, 4, 5 bonds. So here the bonding will be slightly weaker and here very strong. And that is what you've been explained there. So assume a case whereby you have this, let me move slightly up so that so assume you have 1, 2, 3, 4, 5. So that this is full, 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 and this is empty, half filled. Here you'll only form 1 bond, okay? 1 bond here. Here you just form 1 bond. I'm using dots to represent an electron coming from another element. So here you'll have 1 bond, very weak. Here you'll have 5 bonds, very strong. And here you'll have 4 bonds, okay? Slightly strong. So when you have D5, very strong bonds, and we have D5, very strong bonds, less than D5, weaker bonds, more than D, again, weaker bonds. And I think that's enough explanation, because if I explain too much, it will just spoil the flavor of the conversation. So sorry for the background noise. Again, I can't help because I am at home and the kids, of course, are not easy to control. So I think I'll clean there so that we see the writings there. And this is, so when you have D5, more electrons occupy the bonding molecular orbitals, or in other words, more stronger or more bonds form, just more bonds form. So tungsten, which is in group 6, has the highest melting point of all the elements, and mercury in 2b has the lowest. Okay, let's see tungsten and mercury and see where they are in the periodic table. Where is tungsten and where is mercury? Tungsten, tungsten, and mercury. Put that at the back of your mind. Then we see where tungsten and mercury are. Then we see the way forward. So we are looking at tungsten and mercury. I want to clear my clean my board, but it's not clearing anyway. Let's move on. Why is tungsten is W? Tungsten W is here. I'll use my pointer. So tungsten is here. Tungsten, my pointer is hanging again. So tungsten is here. You can see it, W, and the other one is mercury on the far end. And you can see tungsten, which has a very high melting point, is a D5. Okay. If I just move that one S there, it will be D5. Then mercury Hg is D10. It's full. Okay. So electrons have nowhere to go. So you don't get electrons occupying bonding orbitals, and therefore you don't find any bonds forming. And that's why mercury has weak bonds, and therefore low melting point, and that's why it is a liquid, whereas tungsten has the highest. Let's see ionization energies. Okay. Generally, the first ionization energy, you give me a Okay, sorry for the brief stoppage of the teaching. I had to go check on the kids because they're making lots of noise, and of course the noise will reflect in the recording. And I know some of you will be distracted, but now it's part of life anyway. Now let's see. Generally, the first ionization energy tends to increase from left to right. Left to right. Why? Because your radius is decreasing. And as the radius is decreasing, the pull, okay, the pull of the nucleus to your electron is increasing and increasing. So it's just straightforward. We don't need much explanation here. If your radius is getting smaller and smaller and smaller, it means if an electron is here and the nucleus are here, remember how does your atom look like? It looks like that. You have a positive protons there, okay, and you have electrons there which are negative. And who pulls who? The one who is not moving pulls the ones who are moving. Electrons are in continuous motion. They're the ones which are pulled towards the center, not the other way around. So if the radius is decreasing, it means the pull is getting stronger and stronger and stronger, okay? And that's why generally, as you get a smaller atom, you get what? A stronger pull and therefore higher ionization energy, because ionization energy is a reflection of how strongly your electron is pulled. Strongly pulled, higher ionization energy, and vice versa, okay? All of the sixth period elements after lanthanum have ionization energies higher than those of the fourth and fifth in the same group, obviously, because the radius is decreasing, is very much decreasing in down a group in the transition metal. Of course, this is what happens in transition metals, but in main group, it's the other way around. Okay, as you move down a group, they decrease in main group. But in transition metal, the radius decreases and therefore ionization energy is increasing, okay? But in main group, the radius is increasing, ionization energy is decreasing, okay? Here, increase in transition metal. So we are seeing that the lanthanide effect causes what? Lower, uh, lower, causes has an influence on the ionization energy. And I've already explained in this paragraph here. And period 6 elements are so unreactive, okay? Because they are very, very high ionization energies. The lower ones, okay, because this, you can see that from the periodic table easily. And again, this table has just made it clear for you that as you get to the smaller ones, because this is a group, okay, you move down, you're getting smaller because of the lanthanide shrinking. And as you get smaller, what is happening? Ionization energy is increasing. You can see clearly 600, 6. Okay, for this one, it's a bit tricky. Here we don't see the trend so much. We see the trend clearly after here. After the first, here we see the trend. The ionization energy is increasing down the group. The same story there. The same story here. The same story here. The same story here. No, not really. Here, a bit change. a bit of a change, but the sixth one is the smallest and the ionization energy is the greatest. We see an overall the sixth one highest energy level, highest ionization energy. The same story here again. It's continuing now, increase down the group here, no increase up to that point, but the general trend is an increase down there. A general trend, this one has spoiled, but generally the sixth one have the highest ionization energies. I've summarized it there, and we see a table summarizing all the properties we've just studied now. We can see the configuration there, and after the configuration, we see the melting point, we see the boiling point, we see the density, and we see those trends, and we should be able to explain them. Then what about covalent radius? We can see that covalent radius, and again, we should be able to explain why that trend. Okay, the trend should be, why is the melting point increasing across like that? Why? Because the, the radius is getting smaller and smaller. Okay, we can see that there. Then why is the density again increasing? Because you are getting smaller and smaller for the radius. What about the melting point? Why is the melting point increasing? It's because we are getting towards D5, and as we get towards D5, more bonds form or more electrons occupy the molecular orbitals. The same melting point and boiling point trend is seen in this other group, in this other period. You can see again, as I move from left to right in that period, it is increasing up to up to this point. Why? Again, because you're moving towards. No, sorry. This is a bit the same period, sorry. It's not different period. So it's the same period. So as I get to the center, D5, I can see my melting point is almost at maximum, okay? D5, anything that can make a D5 around here, my melting point and boiling points are almost at maximum, but mainly the melting point, okay? Then what about here again? The melting point is now starting to drop because I'm beyond the D5, okay? It starts to drop because am I beyond the D5? Yes, because it's supposed to be D6, okay? So they might not be perfect, but at least we see a general trend that we should be able to explain. Now let's see the chemistry and metallurgy of selected transition metals, and we will select copper and iron, and we will have some general perspectives before we go to specifics. Few metals occur in nature as free elements, that is copper and silver. You can mine gold directly from the river in Ukambani or Western Kenya. Silver, we don't have any in Kenya. We don't have any copper in Kenya, but these three metals, you'll always get them in in free form, that is pure form. You just get gold without any much refining. But it doesn't mean gold doesn't react. It does react, okay? Most metals occur in nature as oxides, sulfides, halides, carbonates, or other ionic compounds. Some metal-containing mineral deposits have little economic value. Why? Because the concentration of the metal is too low, or separating it from impurities is a little bit of a challenge. I mean, a bit of a challenge. Minerals from which elements can be obtained profitably are usually called ores. metallurgy is the name given to the process of obtaining metals from their ores, or it's just the processing of an ore to isolate your pure metal. Few ores are chemically pure. Instead, the desired mineral is usually mixed with large quantities of impurities like clay, sand, and so on. And this is usually called gangue. I think it's a French word. So here you can see copper in a metal, and it is mixed with other things that you call the gangue. And we have a summary of the periodic table here telling us which elements are occur and combined. Of course, this one, okay, and they are very small atoms, small, and they hold their electrons very tight, and they have very low ionization energy, therefore less reactive, and they usually found and combined in nature. Okay, you can see gold is there, and so on. And these are our platinum group metals. Then we can see others that occur as salts, mainly group 1, but our interest today is more of this group, transition metal. So transition metals, either they are free, pure in nature, or they are oxides, or they are sulfides. Those three categories: oxides, sulfides, or pure in nature. Of course, we can be a bit curious for phosphates. So for phosphates, it's only strangely for phosphate, phosphate is which one? It's only the scandium group are the ones which occur as phosphates. Maybe they occur in our fertilizers. Okay, in our phosphate fertilizers, that could be something of curiosity anyway. Now, steps of metallurgy. So the first steps do to remove the gangue, which is just mud or sand, okay? And the second process is what? Convert your ore to metal via reduction, either by use of heat or water. So you can use high temperature, or you can use aqueous solution or wet chemistry to do preparation of your metals. So let us see preparation or production of iron, which is usually produced by pyrometallurgy or heat. Pyro means heating or burning. So it's usually done in a blast furnace. The furnace is charged with a mixture of the ore, which is usually hematite iron oxide. Then you also put in coke, which is carbon, then limestone. Then what next? You put in a very hot blast of air from the bottom of the furnace, and this causes the coke to burn at a very high temperature of around 1500 degrees. And the quantity of air input is controlled so that carbon monoxide remains the primary product. So you limit air so that you don't form CO2, you want CO, the monoxide. So let us see the key equations. So both carbon monoxide and carbon here participate in the reduction of the metal to give you, of the oxide to give you the metal, and CO for the first case. But here, of course, we expect oxidation to get CO2. So, of course, these are redox reactions, okay? This one is oxidized to CO2, while this one is oxidized to CO. And of course, this CO can still be used in this process again, because it's not exhausted anymore. Much of carbon dioxide formed in the reduction process and on heating of limestone is reduced on contact with unburned coke and produces more CO. So again, we can see the carbon monoxide is not wasted, it is recycled by when it comes in contact with the hot coke. Then the molten iron flows down through the furnace and collects at the bottom, and this is called cast iron or pig iron. That's the impure iron, which is very brittle, and uh, impure metal is either brittle or soft and desirable properties for some uses due to presence of impurities such as carbon and sulfur. So this pig iron is very brittle, and it's not so useful because of the properties at that time. So it needs further purification. So what is the further purification done? Let's scroll down and see what purifications are done. So pig iron also contains silicon and silicon dioxide, which are removed in the process below. What is that process? In the process below, what happens? They take calcium oxide as a base and react with the silicon present in the what? In the iron. Okay. Then you get calcium silicate, which is liquid, and it comes out in form of slag. So let us just look at this blast furnace in full and see where these reactions occur. This is where you put in your inflow, the ore, which looks like marram, then coke, then limestone. Then you bring hot air from the bottom. It will rise like that and heat what is coming down to very high temperatures. Okay. Then you generate you heat the carbon, and the heated carbon will react there. Then again, when it reacts, it forms your carbon monoxide. Let me try to expand it so that you can see clearly. So this is the first thing that actually happens. This is our reaction number one, actually. Okay. This is our reaction number one. Then it generates carbon monoxide. Then carbon monoxide again further reacts with that as our reaction two. Okay. Then finally we get CO2. Then CO2 moves upward. As it is moving upward, it comes in contact with carbon, which is falling down. So remember, carbon is falling down. It's a solid. CO2 is a gas. It's moving upward. Okay. If you have a gas and a solid, solids will fall down as gases move upward. It doesn't matter whether CO2 is heavier than air, it will still move upward compared to the solids that are falling down. Ask me, if you have a Coke, a soda, you open your soda, what will happen? CO2 will still pop out. It will still move out in bubbles because it is a gas. Gases will always diffuse no matter what. Okay, so as CO2 moves upward, it meets carbon, they react, they form more carbon monoxide, and this carbon monoxide again goes in the same reaction, and the cycle continues. Okay, and what else have we talked about is the slag. This slag is your calcium silicates. So by the time you finish, you have this slag there, and the equation again is here. Then you get your iron out here. Iron that is much purified, doesn't have silicate or sand in it. So how is it purified? How do you purify your iron further? Okay, because your iron contains all these impurities listed there, and you want to get rid of them. Okay. 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 So your iron contains all those impurities. You want to get rid of them. So what do? You remove by using the basic oxygen furnace, and when you react anything with oxygen, what happens? They burn. So you heat with oxygen, and when you heat with oxygen, these three will give you oxides. Okay. Phosphorus oxide, sulfur dioxide, and carbon dioxide, they'll go out. Then remember, this will have escaped in form of, so as this one escapes as a gas, it can be captured there to form this one, which can be used as fertilizer. Okay. Then at the end of the day, you get what we call carbon steel. And carbon steel can be tempered, or it can be varied its flexibility by heating and reheating. Heating and reheating. So what are the disadvantages of carbon steel? It's not resistant to corrosion, okay? And it loses its properties when you strongly heat them. So you can't use it for strength, rusty applications like building a boiler or a ship. So you need to sort this problem. How do you sort this problem? You have to add some transition metals like chromium, which can be added to form alloys, and these alloys have good properties. For example, we can add chromium and nickel to form stainless steel here, okay? Or we can add aluminum, nickel, cobalt, and copper in those ratios to form what? Alnico, which is used as a magnet for electronics, that is speakers. Then we can actually see the differences in chemistry of our alnico and stainless steel. What is the difference between alnico and stainless steel? Possibly what you've not put there. Like alnico, of course, has nickel, stainless steel has nickel, but alnico has no chromium. Okay. Okay. It has others, like it has aluminum, it has copper in it, it has cobalt in it. Then we can look at carbon steel. Carbon steel has what? Has carbon in it, but yeah, it has carbon in it. And pig iron has all the acidic compounds, phosphorus, sulfur, and some silicon. Okay, so as your own reading assignment, just try to tease out what are the differences between these types of steel, which you can easily get from your notes. Okay, so I will scroll down, scroll down. We see copper. How is copper produced? Okay, copper is produced via different methods depending on the mineral that is being processed. So you have those three minerals, all of them are sulfides, and you're told they're very poor in copper content, and therefore you do what we call enrichment or pre-concentration, whereby you crush your powder you crush your oil into fine powder, then you add soap. The moment you add soap, your ore that is rich in metal will float. And the moment it floats, then you have a separation. And that is you actually use both oil and soap. You know what oil and soap can do together? They'll form something that floats on water, then it picks the copper ore, and the rest of the material sinks to the bottom. Then you get to move this froth or the floating material to the next process. So this picture down here shows what happens, that what floats on top, the froth or the bubbles, will help you to separate your copper sulfide from the denser sand mud that you don't need. Then you can do the hydrometallurgy, which have two of them, two possible hydrometallurgy processes to give you the products. So let us see method one. Method one, if you have enriched chalcopyrite or chalcopyrite, chalcopyrite is here, iron, copper iron sulfide. It is treated with a solution of copper 2 chloride to give insoluble copper 1 chloride, which is easily separated from the ion. The ion which is separated from the ion that remains in solution in form of iron chloride. So I'll just write it here. You have the copper iron sulfide. Then you are reacting it with copper chloride, copper 2 chloride. Then what happens? You get your copper 1 chloride, which precipitates out. Okay. Then the other product is what? Iron 2 chloride, which is aqueous. And where does the sulfur go to? That's our next question. Okay, let's see the equation down here. Yeah, sulfide. Okay, the complete equation is here. Your sulfur precipitates out also. So it means you have two solids, actually. So if you have two solids, then you will have to separate them again. So remember, you'll filter out, but you'll get those two together. Then what happens next? They add aqueous salt, sodium chloride, common salt. Then what does it do? It creates an soluble complex with copper, the chloride ions from sodium chloride, creates a complex that is aqueous, and therefore you are now able to separate your copper chloride from the sulfur. So copper 1 compounds in solution are unstable when compared to copper 2 and copper 0, that's so-called the pure metal, and therefore we expect it to decompose or disproportionate. And when it decomposes, it gives you the metal and copper 2 chloride in solution. So of course your metal is there. Then the other part is your copper 2 chloride. So you have your metal separated at that point. Method 2. Method 2 actually is a method of recycling waste from the mines. So it uses bacteria. So to produce 10% of the copper, actually this method is used to produce 10% of the copper in the United States, whereby here what happens, first of all, acidified water is sprayed onto copper mining wastes that contain very low levels of copper. So as the water trickles down through the crushed rock, a bacteria called Theobacillus ferrooxidans. So you don't have to cram all this, okay? But you just need to understand what happens. First of all, you have wastes from a copper mine. Then you acidify with water to create a medium that is suitable for this bacteria. Then as the water percolates down, this bacteria breaks iron sulfides in the rock and converts the iron to iron from iron 2 to iron 3. So you can see again from the name, it gives us an idea that it is an oxidizing bacteria, oxidant. So, and again, and clearly it's said ferrooxidans, meaning it oxidizes iron. Of course, when iron is oxidized, the final oxidation state is usually iron 3 plus. And that's what we are seeing in this line here. So the iron 3 that has formed now oxidizes the sulfide in copper sulfide to give you copper sulfate. And this makes our copper to dissolve into water. So ordinarily, copper sulfide there with our iron 3 plus to give us copper sulfate. Of course, this is in form of a sulfate. Okay. It ionizes this one to sulfate. Okay, so you get sulfate. Of course, the other part here should be water. So we shall see again if we have that equation in the notes, but if it's not there, we should be able to formulate it, but it's here. So you have copper 2 plus, and this copper 2 plus is in form of copper sulfide. Okay, so forget about my equation here. Not accurate. So it's copper 2 plus here in form of the sulfide. So we neglect the sulfide. Okay. Plus iron. Oh, I've made a mistake. So I ask that you pardon me. That equation I'm talking about is not for this process. So I'll ask you to pardon me a bit. Okay. Okay. So allow me to return here. So here, what do we have? We have iron 3 plus. Okay. We don't know which form of iron 3 plus, but we're told it's iron sulfide in the rock. It breaks down the iron sulfide to iron 3. Okay, so we have iron 3. Then iron 3 oxidizes what? Copper sulfide ion. Okay, that's copper sulfide. Copper sulfide is copper 1. Okay. So it is supposed to be oxidized. Remember, this is copper 1. So when it is oxidized, it will go to copper 2. And copper 2 is soluble. Okay. And it has caused oxidation. Okay. So iron is the one that is doing oxidation. So iron will go to iron 2 plus. Okay. And we are told the sulfur is converted to what? To sulfate. Okay, like that. So we should ask ourselves, where is the oxygen coming from? At least we know the sulfur. So the oxygen must be coming from, possibly from air. So we can put there oxygen from air. And this is carried out again under the conditions of the bacteria. Then in the next step, what happens? The copper 2 plus reacts with the ion provided. Okay. So you get iron metal, pure iron metal now, which now reacts with your copper to aqueous to get you those products. It's a bit a long story, but it's fine. We have to learn. We have no choice. Okay. So the last method is when you have copper sulfide. And again, what you do, you just do the frothing. You crush in air, you do the frothing, you get your mati, which is copper 2 sulfide. Then what do you do to your copper 2 sulfide? It is hot air is blown through it, okay? And when hot air is blown through it, you get your copper metal and sulfur dioxide gas. However, now you need to purify it further by subjecting it to electrolysis. And in this electrolysis, you get your metal immersed in a mixture of copper 2 sulfate as your electrolyte and sulfuric acid, so that now you end up with copper being dissolved from the impure cathode and deposited as pure on the, dissolved at the anode. So your anode is made up of the impure copper and your cathode is made up of pure copper, which means what is happening that your metal is dissolving here in form of copper 2 plus and migrating for depositing on the cathode. So of course we know cathodes attract cations. That's what happening. That's what is happening in this case. Okay, so that is what is happening in this case. So I'll move. I think I'll just give brief explanations because all of us know all that. Okay. So now we get to a point whereby we need to learn about chemistries of selected transition metals. And again, here we select another 2 metals. Remember, we've just learned about metallurgy. We selected 2. Now we need to learn about the chemistry. And again, we just select 2. And in this case, we'll select copper